Hello everyone. Thank you for the introduction. I'm Yo from University of St. Andrews. So welcome to the very last talk of the very last sessions. I think maybe the organizer keep the best talk to the last. Maybe I'm just joking. So, okay, I will present on RadarCat, which we use a radar and a cat to categorize the objects and use it for input and interaction. No, without the cat. So I'm not sure about you guys, but when I think about the word radar, I will think about this huge radar dish, or this military radar operated by the operator, or even this weather radar information. However, today, I'm actually want to talk about this kind of radar. Yes, this is actually a radar. For those who don't know about this is a radar on a chip. It's called SOLI. It's made by Google RTAP team. So you can see it's very small compared to the coin here. And it is a 60 gigahertz frequency modulated continuous wave radar. And it is monostatic, which means the antenna, the transmitter, and the receiver are placed together. And it has 6 antennas in total, which supports up to 8 channels of operation simultaneously. So this radar was designed to detect the micro finger motion to enable the gesture interaction with a wearable device. And in fact, Google has shown that they have successfully embedded this small sensor into a smartwatch. There was a demo 2 days ago by the SOLI team. Not sure if you guys have tried it out. But right now, I don't have this watch yet. I have this. This is the SOLI Alpha Developer Kit. It is slightly bigger, not that small, but still quite small. But actually, the real radar chip is only the red dotted line area. So how does this SOLI radar work? So the sensor emits the radio wave. And when the radio wave hits the target, some of them get scattered and some of them get reflected back to the sensor and get measured. By doing this in a very fast manner, it can track the micro finger motions. When it is able to detect this micro finger motion, it can enable a range of different micro interactions, such as a virtual button in the air, virtual dial, slider, or virtual trackpad. Okay, but I'm not doing any of this. So I use this SOLI radar to achieve objects and material recognition. So this short video clip, it was shown in Google I/O this year. But by that time, our team was able to only recognize a few very unique material. But since then, I have upgraded the system and able to detect more objects and material. So I'm supposed to do a live demo because my advisor insists me to do so. And I will invite my assistant, lovely assistant, to come and help me. Okay, I hope everything still works. Camera. You're using a webcam? Okay. So it looks like a toy store here with a lot of different things. Can you see those objects and the screen? You can see the screen, it's not clear.
Oh, there we go.
Okay, right now it's a predicted air because there's nothing on top of the sensor. So if let's say if I put a sponge here, it will say a yellow sponge. It's inverted.
It's inverted, yes, this is fine. I know, it's okay.
Okay, let's try something else. This is a red eraser over there, red eraser. And let me try something else, maybe a book. Okay, it says a book. A case book. Let me review the clutter map. Okay. If I place a silicone case, smartphone case, and then maybe a steel. Say a steel. And last one, or last two, sorry. Say this is a phone, Nexus 5, facing up. If I flip it and face down, it should say Nexus 5 facing down. So one last thing. There are two cups here, one with water and one without water, although I'm not allowed to bring water here. Okay, it says empty glass, and then when I pour in the water, it should change immediately. Yeah, it says glass with water. Okay, that's all for the live demo. Thank you for my lovely assistant. Okay, I can skip this video. Okay, before I go into the technical details, I want to talk about why I think this is important or useful. So if we can recognize everyday objects, we can use it to interact with computer. It can enable tangible or more natural interactions. Also, it can enable the placement-aware interaction or using the body shortcuts. Finally, it can automate a lot of different processes, such as sorting waste in the recycle center or quality control. But of course, there are a lot of different technology that can achieve the same thing, if not better, such as RFID tag, the vision marker, barcodes, or spectroscopy, or even computer vision techniques. That's why I want to highlight on our contribution, which is we support the recognized everyday objects, the untagged everyday objects. Also, our technique is not limited to the surface detection only because the radar signal is able to penetrate through certain material. Finally, our system works in real time for interactive application. So there are a lot of related works in this field, so I will be mostly focusing on only the untagged objects. Using light sensing, it is possible to detect the different material and even the transparent material. Using the electromagnetic noise, MSense is able to detect what the user is touching or holding, and using EMG signal, it's possible to detect rich body parts. Using vibration, it's also possible to detect where the object is placed on, such as a desk or a chair. Something as simple as using just a wave, just by measuring the wave, is also able to guess what is the object. Finally, using a combination of these different techniques, it can even improve the accuracy. In terms of radar, there is something called ground-penetrating radar, which can tell what kind of material is buried inside, underneath the ground. In Mobicom last year, the author showed that it is possible to reusing the 60 gigahertz radio to detect some material from a distance. Finally, using an even higher frequency, such as a terahertz imaging, it's possible to look inside the material, different layer of the material. Okay. So this is how our system works. By placing an object on top of the solid sensor, we get the raw radar signal and we extract the feature, we pass it into a machine learning and training, and then classify the object in real time. So this is a working principle. Because Solid is designed to detect finger motion, so you can see the signal here is highly sensitive to any finger movement. However, when we place some object on top of a sensor, the raw signal is actually very stable. And more importantly, the signal shows a different characteristic for different kind of material and objects. Therefore, we can exploit this different unique signature for different objects and recognize them. So this is not a very nice visualization, but when the solid emits the radio wave, it hits the targets. Some of them get scattered and some of them get reflected back. But as I said, radar signal is able to penetrate through some objects. So there is also internal reflection and internal scattering, and finally get reflected back to the sensor. Which this gives us a very unique radar signal for different kind of objects. As you can see here, some sample raw signal. You can see that different material has quite a different pattern. But let me zoom into some of them. For example, aluminium and steel. They have quite similar raw radar signal, but we can still observe some difference here and there. Therefore, we can exploit this to recognize the different material. But what very interesting to me is the empty glass, like you've seen just now. Empty glass and the same glass with water, it shows very different radar signature. Okay. Also, porcelain plate and ceramic plate, they look quite similar, but still there are some difference. So we extracted the 8 channels raw data, which consists of 512 points, 12 data points. We also extracted the average channel and the absolute channel. Finally, we also extracted 21 other features, and we trained it using the random forest classifier. The details is in the paper, so please check the paper. So our machine learning pipeline is a quite standard one. We place the objects on top of the sensor. We extract the raw radar signal. We label it and pass it for training. After we train the classifier, we can use it to recognize the object in real time for the application and the UI. So we conducted 3 experiments to evaluate this system. The first one is 26 objects found commonly in the office and kitchen. Some of them here. So we collected 6 rounds of data twice a day for 3 days. Each time we place the object on top of a solid sensor, and we place it for 10 times at slightly different position and orientation. And then we evaluate using the lift one out process, and the average accuracy is 96%. So I will not go into the details, but I want to highlight on some of them. For example, the book and the wood have some confusion. I think it's because they are made from very similar material. Also, aluminium external hard disk and a scale have some confusion, like here, because they have very similar material on the outer casing. The second experiment is 17 transparent materials, including air. So the result is very accurate, and in fact, we were surprised by this result. There is really nothing much to discuss about this result, but we were really surprised that using this radar signal, we were able to differentiate not only the different materials, but also the same materials with same thickness and different thickness, and even different color. Finally, in the last experiment, we test on 11 body parts. We use the solid sensor as if using a stethoscope and point onto the different body parts. So this is the result. I want to highlight that for some of the body parts that looks quite different, like the palm, the finger, they work quite well. Also for the body parts that are covered by clothes, like the shirt, the pants, they have very high accuracy. However, there are several body parts that have very high confusion, such as the forearm, the belly, and the calf. It is because the radar signal can penetrate into the skin about 1 millimeter. That's why these three body parts, forearm, belly, and calf, they appears to be quite similar in the point of the view of the radar. That's why it has some confusion. But in the future, if we can try using a different frequency which can penetrate into the human skin deeper, we might be able to improve the accuracy. So now I want to show you some application. So we can consider a learning application of physical dictionary where you place the apple or orange and it tells you all the nutrition facts or even the language translation. So it might help the children for learning. We can also consider the shoppers comparing different font models, and the detailed specification is shown on the screen. We can also make the tangible painting application. We use a solid facing down as is using a probe. By touching different material or material with different thickness, we can change the brush size or the operation mode and even changing the brush color. So we can also enable body shortcuts and context-aware interaction. So as you can see here, the user is holding the smartphone on the glove hand. It makes the button bigger to help the user. It can detect forearm, finger, the back of the hand to launch the clock application, the outerwear jacket, and the stomach to launch the foot application. And then the shirt, the pants to launch the map, and finally, cuff. Okay, in the restaurant scenario, you can automatically refill when it detects the cup is empty. So I'm running out of time. I should end this soon. So I think we are just barely scratching the surface of this radar sensing, and there are a lot of future applications, such as here. I don't have time, so. But I really need to say huge thanks to the Google Solid team for providing this hardware and the software support. And without them, I think this project would not be possible. So thank you very much, and I'm open for questions.
Okay, we can ask a few questions. So I've got one. So you were training with the same object over and over again. How robust is it to multiple instances of that thing? Like if I train on my palm, does that work for your palm as well?
If it is the same model, it should work. But if it's a different model, then we need to train first to make it work. For now, it will not recognize the new objects, and which is our future work. We plan to keep a large database and recognize the new objects. So.
Okay, back here.
Thank you.
Hi. Of the font. So if you put, can you detect, recognize the font independent on, which part of font you put that, radar?
Okay. This is a very nice question, which is actually, probably I shouldn't say this. We are trying this and we submitted a new paper based on this one, detect the different location of the font. Because the font has different components, like you say. Each location has different signature. We can use it to detect the location. Yeah, so it's possible, yes.
Oh, okay. Is it so possible?
Yes, it's possible.
Yeah.
Okay, one last question.
Thank you. It is a really awesome idea, and I'm just wondering, there is some relationship between weight of object and recognition rate.
Weight?
Weight.
How heavy?
Yeah. I'm just wondering.
I think there is no, because this is radar sensor. This is not a waving sensor.
Yeah, no,
but actually,
yeah.
I think we can combine different type of sensor using the wave with radar or even light to make it even more robust and more accurate. But right now, I'm not using wave at all.
Thank you.
Thank you.
Okay, let's give all our speakers one last hand.